Welcome to another lecture in the PHAY0032 series on pre-formulation. Today we're going to talk about amorphous materials, which is one of my favourite subjects. So I've got my cup of coffee ready as ever, and I highly recommend that you do too. If you need, pause the video while you go and make a drink. Once you've got one, come back, press play, and let's begin. What do I want you to learn by the time this lecture is finished? The first thing, clearly, is what is an amorphous material. Within that, I want you to understand where the molecules are and what they're doing. With time, an amorphous material will change, and that process is called relaxation. So by the end, you should be able to describe to someone what the process of relaxation is and how it affects how an amorphous material will behave. There is one key transition point for amorphous materials, and that's called the glass transition temperature. So you should be able to describe what a glass transition temperature is, and you should be able to discuss what happens to the molecules at the glass transition temperature. A couple of final things: we can make materials amorphous with certain processing techniques. So by the end, you should be able to say which techniques make materials amorphous, either deliberately amorphous or accidentally amorphous. And the last thing is to be able to discuss in some detail how a material being amorphous affects how it delivers drugs to the body. On the screen in front of you are two materials. On the left is sugar cubes and on the right is candy floss. Why are these two materials here? The answer is that they both contain the same molecule, in this case sugar, or more specifically sucrose. The difference between these two materials is that the sugar cube is crystalline and the candy floss is amorphous. Why am I starting a lecture like this? The reason is because I want you to see that although the molecule is the same, sucrose, the way that these materials behave is completely different. If you took a cup of tea, hopefully that cup of tea that I asked you to make a little while ago, and you added a sugar cube to that cup of tea, what's the next thing that you have to do once you've added a sugar cube? I'll give you a couple of seconds to think about it while I drink my tea. Nice. The answer is you're probably going to have to stir it. Don't believe me? I happen to be downstairs and I've just boiled some water. So here is some steaming hot water representing my cup of tea. And here is a sugar cube. So let's imagine that you are not like a builder. You just want one sugar cube in your tea. So let's put the sugar cube in. I hope you can see, it's a little bit far away, the sugar cube is not dissolving. And the reason is because it's a crystalline material. If we want to get the molecules into solution, we have to break the bonds that are holding them in the crystal lattice. For a cup of tea, since we want the sugar to dissolve before the tea gets cold, the easiest thing to do is to stir it. I have long wondered why when you go to a coffee shop they give you these really long spoons, but I understand now, it's so you can get to the bottom of a really tall beaker like this. So let's stir, and as we stir we're applying some energy to the system, and that energy helps to break the molecules off the crystal lattice, and so it dissolves faster. So hopefully you can see that almost all the sugar has now dissolved. Now let's think about the candy floss. Imagine when you go to the fair and they make a big load of candy floss for you. You put that candy floss into your mouth. What's that first feeling that you experience? Again, I'll give you a couple of seconds to think about it. Hopefully the word that you've said out loud to yourself is melting. It feels like the material melts in your mouth. Now, as we'll see later, amorphous materials don't actually melt, but it's not a bad use of the word. You put the material in your mouth and instantly it disappears. The reason it does that is because the molecules in an amorphous material have no crystal lattice energy holding them together. So as soon as those molecules come into contact with water, they can instantly disperse. Another reason that the candy floss appears to disappear is because the molecules in an amorphous material are not very well structured. So in a crystalline material, the molecules are next to each other in a repeating pattern, and that means there's not a lot of space between the molecules. In an amorphous material, on the other hand, the molecules are very randomly dispersed, and so there's a lot more space between them. That means that amorphous materials often have a much bigger volume than a crystalline material, but a much lower density. So when you put the candy floss in your mouth, it appears to disappear because the molecules are dissolving and all that space goes away. So the reason I've started this lecture with these two materials is simply to say there's no chemical difference between these two systems. They're both made of sugar. The only difference is that in one side we've got crystalline material and on the other side we have amorphous. If we think about what that means for dissolving these two systems, the crystalline material goes into solution very slowly, whereas the amorphous system goes into solution much faster. Think about what that means for pharmaceutical products. Wouldn't it be better, since we want fast-acting products, for all of our systems to be formulated in the amorphous state? And that would be true. If you make a pharmaceutical system amorphous and someone swallows it, it will dissolve a lot faster. What that means is you should get an increase in blood plasma concentration fastest with an amorphous system. Think about the sorts of medicines that you might buy in your pharmacy though. Can you think of any that are amorphous? Probably not. And the reason is because the pharmaceutical industry is a very conservative industry. It cares above all about the stability and safety of its products. Think about the candy floss. Imagine you bought some at the fair and you put it in your kitchen cupboard to save for another day. Do you think it would still look like candy floss when you got back to that cupboard? Probably not. All it needs to do is absorb a little bit of water from the surroundings and it will crystallise on storage. Think what that means for a pharmaceutical product. Imagine that the way it behaves is critically dependent on all of the drug molecules getting into solution. And the reason it gets into solution is because it's amorphous. Imagine that product then crystallised on storage. It's not going to work when a patient takes it. It's much safer if you're going to store your product for a long period of time that the material is crystalline. And that's exactly what we find for pharmaceutical products. Although we can make them act faster by them being amorphous, because it's a conservative industry and stability is more important, most products are crystalline. That means that when the consumer leaves those products on a shelf and comes back to them a few years later, it still behaves the same way. But the key thing here is the only difference between these two systems is the physical form of the material, the way the molecules are packed together. And we can fundamentally change how quickly those materials dissolve simply by changing their physical form. On the screen in front of you is a graph that I hope you're familiar with by now. It shows you what physical forms are available for small molecular weight organic compounds. Starting at the top, we have two options. The molecules can either repeat in some sort of pattern, in which case the material is crystalline, or the molecules can be randomly distributed, in which case the material is amorphous. For materials that are crystalline, it's possible to subdivide into further categories. If there's only drug substance in the unit cell, the material is polymorphic. And if a material can be polymorphic, it can have either monotropic or enantiotropic polymorphism. If water is in the unit cell, the material is a hydrate. If solvent is in the unit cell, the material is a solvate. And if there's anything else in the unit cell which is ordinarily a solid at room temperature and pressure, the material is a co-crystal. Within that, materials can be both reversible and non-reversible. So you can see we have a number of different options for crystalline materials. And even if we consider the shape of those crystals, they can have different habits. It's not possible, for instance, to tell which polymorph a material is by looking at the shape of the crystal, because different polymorphs can have the same habit. So crystalline materials are hugely complicated and have lots of different physical forms. Now look at the graph for amorphous materials, and you'll see all that's written is the word amorphous. And the reason for that is because amorphous means no structure. Because we have no structure, there is no way of subdividing that any further. So an amorphous material is just that, randomly distributed. It's either amorphous or it is not. On the screen in front of you is a graph that I hope by now you're quite familiar with. It shows you the formation of crystalline materials. So how this works is, when a material is molten, the molecules are free to move. Because they're free to move, the material has a high energy and or a high volume. So on the y-axis of this graph, written energy or volume, just depends how we want to talk about it. So if we start from the liquid state, the material is at a high temperature. So the x-axis on this graph is temperature. As we cool the material down, the molecules start to move with less energy, and so they start to come together. So the energy and volume of a material decreases as the temperature starts to drop. When we get to the melting point of the most stable crystalline form, there will be a discontinuity. And what that means is the molecules are going to come together to form a crystalline lattice. Because it's the most stable crystalline form, by definition, it's the one with the smallest volume and or the smallest energy. And so there's a drop on that graph as the material crystallizes. Once it's formed that crystal and we carry on reducing the temperature, there'll still be a small reduction in volume and energy. So we get a graph that looks like this. It's really important to recognize that if that material is the stable polymorph, it means the polymorph in which the molecules are most perfectly packed. What that means is that the stable polymorph should always have the lowest energy and the lowest volume of any material. We need that concept later on, so remember it for now. The next thing that's shown on this graph is what happens if we don't give the material time to form the most stable polymorph. So again, if we start on the right hand side from a liquid state and we start to cool the material down, for all of those molecules to condense to the most stable polymorph takes a bit of time. Every molecule has to come down, orient itself, and then join to form a crystal structure. If we carry on cooling a bit faster and we don't give the material time to crystallize, the molecules don't have time to form this perfect pattern. And so they carry on in a liquid state. But it's a liquid state below the melting point of one of its crystalline forms. And that has a special name. It's called a supercooled liquid. So a supercooled liquid is shown on this graph. And it's a very unstable state because the material wants to do something. If there are other polymorphs available, the material will crystallize to one of those polymorphs. The reason it goes to a different polymorph is because, not being the stable polymorph, it must be metastable. And metastable means less well packed or slightly higher energy. So in other words, it's an easier state for the molecules to get to. So in this instance, we form a supercooled liquid, but when we get to the melting point of a metastable form, the molecules then condense to form the metastable polymorph. And again, we see a discontinuity as the crystallinity is formed, and then it carries on reducing in volume and energy ever so slightly. In this instance, that's the metastable form, which means it has a higher energy or higher volume than the stable crystalline form. So that's the graph that you've seen before, and I hope that you are familiar with that type of explanation. If I asked you to go and look in a textbook and tell me what the definition is of the amorphous state, you probably won't be able to. And the reason for that is because the amorphous state is widely studied but poorly understood. Partly that's because the amorphous state is by definition random, and random is very difficult to define. What that means is we're going to talk about my view of the amorphous state, and you are free to form your own view so long as it's a sensible view. Many of the terms that we're going to talk about originate from the polymer field, and the reason for that is because polymers are large molecular weight compounds that generally are either amorphous or semi-crystalline. Another thing that's really important with amorphous materials, especially for pharmaceutical products, is that many people don't recognise that their material might be amorphous. It's very easy to think that a material is either completely amorphous or it's completely crystalline. But there are lots of processing techniques that we might use that make a material partly crystalline. So if I give you an example, you're probably very familiar with the way that tablets are made. You take a crystalline powder blend, it's in a hopper, some of it gets put into the punch and die, the punch and die compresses, and we end up with our tablet. What you may not have considered is the force that's being applied to that material is very high. And it's quite possible that as the punch and die come together, some of the molecules at the surface of that tablet become disordered and so they become amorphous. So although the tablet itself is predominantly crystalline, if we were to look at the surface, some of the regions may be amorphous. One of the reasons that people get a bit unstuck when it comes to the stability of materials is because they don't recognise that some of the material might actually be amorphous. Another way of looking at that is to say that there are certain techniques that nearly always make a material amorphous. Freeze drying is one, spray drying is another. So if you're working for the pharmaceutical industry and you're spray drying something, your mindset is that the material is probably going to be amorphous, and hence you're going to look for it at the end. But if you're making tablets with a tablet press, you're expecting the material to be crystalline, and so you're not looking for amorphous materials. So one of the key things to take from this lecture is to understand how amorphous materials are made and to recognise that they may influence how a product is performing, even if there's not a lot of amorphous material there. So I said amorphous materials are difficult to define, but I'm going to have a crack at defining them anyway because I think we have to. The first thing to recognise is that the word amorphous itself comes from the Greek language and it means lack of form, so it's a very descriptive word. There are many ways of describing amorphous materials and I'm going to give you my favourite one. And the way I like to think about amorphous materials is they are high viscosity liquids. What that means is when we look at where the molecules are randomly distributed, exactly the same as if it was in a liquid. The difference between an amorphous solid and a true liquid is that the solid is highly viscous. What that means is if we look at it at one point in time and we see where the molecules are, if we look at it again 5, 10, 15 minutes later, the molecules are still in the same place. If we did the same thing with a beaker of water, for instance, the molecules would have been completely moved about. So the difference is an amorphous material has the structure of a liquid, but it has the viscosity of a solid. Have you ever come across an amorphous material in real life? Now, I don't know about you, but I'm looking at you through an amorphous material. So here, glass is a classic amorphous material. Have you ever wondered, for instance, why I can see through glass and yet glass is a solid? And the answer is because in a crystalline material, all the molecules are arranged in the same pattern. So when light hits a crystalline material, some of that light gets refracted back again and the material is not translucent, so you see a solid colour of material. With glass, on the other hand, the material is amorphous, which means that the molecules are randomly distributed. So when light goes through glass, some of the light gets refracted back, which is why you can still see your reflection in a glass window, for instance, but the majority of light passes through, and so you can see through the material, even though it's a solid. Now, there are some other classic examples of materials which are amorphous. So one of them is shown on the screen, and I happen to have some over here. Jelly babies. You can go to the sweet shop and you'll find hundreds of amorphous products. You can tell this is an amorphous product, by the way, because it's a solid. That's fine. But also, if I apply some force to this material, you can see that it moves. So although it's a high viscosity liquid, it's still really a liquid, and we can deform it in the way that we can't deform a crystalline material. Nice. On the screen in front of you is the graph we saw earlier. It shows you what happens when a material forms a perfect crystal. We start at a high temperature with the molecules in the liquid state, and we cool the material down. As we get to the melting point of one of the crystal forms, the molecules condense to form that crystal, and we see a discontinuity. Then we have a new line which represents the stable crystalline form. And I said earlier, it's really important to recognise the stable crystalline form is that form where the molecules are perfectly structured. That means it should have the lowest energy and the lowest volume. When we looked at this graph earlier, I said if we overshoot the melting point of the stable crystalline form, we form a metastable liquid, and that's an unstable system. When we discussed it earlier, I said if there's a metastable form available, the molecules may condense to that different form. On this graph, what we're considering is cooling the material really, really fast. It doesn't matter which crystalline form the material can go to, it still requires time for the molecules to orient themselves and condense. If we cool the material really fast, we create a supercooled liquid and it stays a supercooled liquid. The only question to consider is what happens to that supercooled liquid as we reduce the temperature. Is it the case that the supercooled liquid carries on cooling down forever? And the answer is no. And the reason for that is because at some temperature, the volume and energy of our supercooled liquid will go below that of our crystalline material. Now that's called a paradox, and it was named after the man that first thought about it, who was called Kautzmann. So it's known as the Kautzmann temperature, or TK, as shown on my graph. It's the point at which the supercooled liquid would in principle occupy a lower volume and energy than our stable crystalline form. If we make this measurement for real, something has to happen to our material to prevent this paradox from occurring. And what happens in reality is that the material goes through a discontinuity, and that is represented by the breakpoint on the line. The temperature at which that discontinuity occurs is known as the glass transition temperature, or TG, as also shown on my graph. And it's a really important temperature to understand. The question is, what happens to the material as it goes through a TG? And this is a little bit of a tricky concept, so I'm going to explain it, and then we're going to stop the video for a while you have a think about it, and then we'll return to it in part 2. So the way I like to think about it is this. On the right hand side of this graph, at a high temperature, the material is behaving as a liquid. That means the molecules are all randomly dispersed and free to move around. As we cool the material down and it becomes a super cooled liquid, the material is still a liquid and the molecules are free to move. However, as we cool the material down, the energy and volume of the material is reducing. Because the volume is reducing, but the number of molecules in our system is remaining the same, the distance between those molecules must start to get smaller. Therefore, if the molecules were free to move around and not hit each other, as the temperature reduces, you have the same number of molecules in an ever-decreasing space, and they start to bounce off each other. What that means is the viscosity of that material starts to rise. So one way of thinking about this is that your material is a liquid, but as the temperature is reducing, the viscosity is going up, or in other words, the material is getting thicker. One interpretation for the glass transition temperature is to say that above the glass transition temperature, if we change the temperature of the material, although the material is viscous, the molecules will move. So, imagine that I hold the material just above the glass transition temperature and I increase the temperature slightly. The material will become less viscous because the molecules can move. Similarly, if I reduce the temperature slightly, the material becomes more viscous because the molecules are less able to move. As we change the temperature, either up or down, the material is responding. And so the material is said to be in structural equilibrium. If we change the temperature, there's a change in structure. When we go below the glass transition temperature, this is a key point, and it's a key point because the viscosity of the material becomes so high, as we change temperature, the material can't move. The material is said to be out of structural equilibrium, because if we change the temperature, there is not a concomitant change in structure. There are some special words that people use to describe these states. Above the glass transition temperature, the material is said to be rubbery, and below the glass transition temperature, the material is said to be brittle. Now, I said earlier that some of these terms are coming from the polymer industry, and this is a really good one. No one would look at pharmaceutical material and describe it as either rubbery or brittle. They apply to things like rubbers and things like that. But these terms originated in the polymer industry, and they've stuck in the pharmaceutical one. So to sum that up, the glass transition temperature is a breakpoint, and it's a really important breakpoint. The point itself is where the viscosity of the material becomes so high, the molecules are not able to move. So the way I like to think about this is when the material is above the glass transition temperature, it is a rubbery liquid and the molecules are able to move, but below the glass transition temperature, it's a brittle solid and the material is not able to move. So hold those thoughts in your mind. We're going to take a quick break and you're going to have to answer some questions before you can watch part 2.